So yeah, our final speaker is from Mentor Graphics, a Siemens business. And the title of the talk is How Formal Reduces Fault Analysis for ISO 26262 Safety Verification. Abdel Ayari, PhD, is an application engineer for formal verification, clock domain crossing, and low power verification. He received his doctorate in formal verification at the University of Freiburg and worked for Micronas GmbH before joining Mentor, a Siemens business. And he's speaking from Munich today. So handing over to you, Abdel.
Yeah, thank you. Thank you. Yeah, many thanks for previous talker. So I will present here some work done by my colleague Doug Smith. I want to show you how can you can use formal to reduce fault analysis for ISO 26262. So I will skip a lot of motivation stuff that we have already seen here on from previous talks. I will jump directly to how formal can be used, and the content is how formal verification can help you to prone reduce the fault list, how you can use formal itself to inject faults, what kind of results you can get, and how you can use other solutions to complement the formal approach. So the first thing is actually when we are talking about formal is that formal is like it's like simulation is elaborating the design, is creating is what we call a net list. In this process, the formal is applying whatever kind of setup is necessary, and it is tying off all relevant non-relevant functional modes, is ignoring all unconnected, is building an optimized formal net list. Then the formal tools today have opportunity or utility to get the fun and cone of any design element. You can specify a set of signals or a set of set of registers, whatever, and you can ask for the the cone of influence of that. So you can use this just to generate the fault list for your safety goals. You can also use this cone of influence to generate the cone influence of your safety mechanism. You can then, based on what you are interested on, single point or residual faults, you can combine these faults to consider them as your starting faults list. So here's an example that we have that we are working with some customer here. We have a design with a 1.7 million gates. The cone of influence, when we apply the cone of influence, we have a reduction of 18%. And when we do further other techniques like fault collapsing and others, we get a further 28%, so that in total we have 2%. So actually it is a dramatical reduction here, and we are, so it is necessary to do this kind of fault optimization. For the key or the basis for this is actually what the tool provider or the tool is providing you as a utility. Here in QuestaForm we have what we call formal cone of influence, and you can ask the tool to give you the cone of influence of any signal. And then you can, of course, you have another opportunity, another utility also to ask for the fault cone of influence of the CVT mechanism or a set of signals. So now, after using or optimizing the fault set, I want to explain how you can use Formel for fault injection itself. And there is the three questions that we want to answer is that how you inject faults, how you write your checkers, and which kind of tools you want to use. First thing is actually very simple. Today, in Formel tools, you have what we opportunity cut any net in your net list, from net list, and force the net with some value from outside. And this is the key how you can model faults. Here is some examples for different fault models. For example, if we have stuck odds, you can cut the net and use some constraints to add to force 0 or 1, depending if it's stuck at 0 or stuck at 1. If you have a transient or CU, you can do also the same. You have to cut the net and provide some signal to force the transient behavior. Similar for open. The main drawback, if you do this, is that you have to specify this cut points at the compile time. So it means you have to know which faults you have to consider, and then you have to provide this for your compilation. And the tool has to every time when you need to consider another fault, then you have to compile everything from scratch. So this is not necessarily efficient, and you will lose a lot of time in compilation time, but a lot of resources, a lot of database will be generated. It's not efficient at all, and what you need is actually to have a possibility to run Formel compile for all faults at once. And then later you can run the verification steps for all faults if you want, or for different faults. This is done in Quester form using what we call conditional cut points. It's actually, and this is conditional cut points is a cut point is a signal with a condition and the driver, and this condition gives you when to cut the net, and the driver is actually give you logic that will drive the net when it's cut. If the condition is not taking place, then you are actually driving the same value as before, so as there is no fault injection. So using this mechanism, you are enabled, so at compile time, you are enabling to compile all faults at once. Here is an example. We have 3 fault sites, and the first one is we are driving 0, some faults stuck at 0. The second one is stuck at 1, and the third one is in a transient fault. So at the compile time, you are only specifying what kind of faults you have and the fault model that you have, and this will compile at once. With this technique, we were able to compile the CPU design that we have with 1.7 gates and with 1 million faults within 1 hour. So it's actually a dramatical reduction of compilation time. So now the next point is how to check the fault, how to detect that faults can affect your safety goals and so on. So here we have a design with safety goals and safety mechanism and some faults at different locations. bundle of signals actually in general. The question that you are interested on are actually, are there faults that are undetected on safety output in the mechanism? So this is what we call UU case. Are there any faults that are undetected on safety output but detected by safety mechanism? UD kind or category. And then the fault, are there faults that can be detected on safety output but not detected by safety mechanisms? And the last one is, are there any fault that can be detected on both the safety output and mechanism? Of course, here actually the most dangerous one that you want to make sure that you can capture them are the faults that that are detected on safety output but not detected by safety mechanism. So how you can write this or put checkers for that? There is actually two ways to do this. There is a way using property checking. For this, you can use, this is assertion-based approach. You have to write the assertion that model how the fault can be detected on the safety mechanism in the safety goals. Maybe you have also to add some system level assertion or PSL assertion to restrict the design to some specific behaviors. In general, I can say that the effort to write assertion can be challenging, can be high, but it depends, of course, on the fault models and the design that you have. Things are much more simpler if you are looking to, or you are using sequential logical equivalence checking. In this approach, there is you provide two designs. This is actually the same design. One copy will be used as a reference, and the other one will be used for fault injection. The assertion that you want to write to check the safety goals are actually here simply a list of mapping points. Also, if you have a safety mechanism and you want to restrict the behavior or the paths that are of interest to those that are corrected by the safety mechanism, this is also very simple to address using some simple list of mapping points. If you maybe tell that we'll say that this we will get more higher or increased runtime for Slack versus property checking. That is not necessarily the case because here we are comparing two more or less two identical designs, and Slack today have additional technology that can identify internal equivalent points that can be used to check if the safety goals are equivalent or not. Here is a little bit in picture. I said before, we have two copies. One is to inject. So I don't have a pointer here. I think I have a pointer here. So this design is to inject faults. The other design is actually used as a reference. This is a safety goal. We want to check that the safety goals are same as behaving the same, that is no divergence. And when we have safety elements, we want to say that the paths that we are interested on are actually, how to say, if there is any faults in the path that we are interested, that will be covered by, checked by the safety elements here, by the safety mechanism. So the safety mechanism points here we are used as a kind of assumption, and so we in our tool here we have only just a list here. This is actually automatically produced by the tool, where we say just filter out all the paths that are detected by the safety mechanism and check only the paths that are that can violate the safety goal. Okay, so in the next, of course, here, when you run this, your fault injection in Slack, you get debug environment where you see where faults are, let's say, are injected here, and where the fault, where the outputs or the safety goals are diverging. Sometimes later. In this case, we are actually we have stuck at 0 for fault with ID 10, and we are doing fault injection at, sometimes after initialization. This is something that can be configurable. You can instruct the tool to do immediately stack at injection after initialization. Okay. Yeah, when you run form, then you have some coverage, some results. You can report the number of safe goals, the number of unsafe goals. What are the faults that are hard to decide, and of course you have a regression of running this Slack application, and you have maybe some runs that are not done so far. So you can get a report telling you at the end what is done. Okay. So the next question is, what happens actually if you are if we are not able to achieve everything with formal verification, or if you are considering software safety mechanism. So the safety mechanism that we have talked about, hardware safety mechanism. Now the software safety mechanism are actually subject for other verification solution like emulation and simulation. So here again, you can if you start with formal, the undecided fault can be forwarded to the fault verification solution that we have, simulation or emulation, and from there you can start analyzing the rest. At Mentor we have the Mentor emulator, which has a formal app that can take the formal list with the corresponding injecting time points and can do the fault injection for you and gives the results. Even if you don't start with formal and you are actually using only simulation or emulation here, the formal tool or the formal utilities that optimize fault list is necessary, because it gives you optimized fault list, and then you don't have to spend a lot of work doing fault in place that does not have an impact on your results. At conclusion, I have we can say the fault form can help you to identify faults, optimize them. You can even do fault injection with formal. Formal is exhaustive, so it's complete. At least all the safe, all the faults that are proven to be safe are really safe. The unsafe faults, it can be because lack of constraints. This is something that you can add. You can add to your formal environment constraints to address them, or you can pass this unsafe, let's say, unsafe faults to the simulation and see if it can be addressed there. It can be confirmed to be unsafe. But usually in the formal context, you have an environment where you can add constraints. We have seen this before in the talk from Jörg from OneSpan, where the safety mechanism, some signals for the safety mechanism has to be set to some value. Of course, you can do this, and you can correct the results. Formal verification is also used to optimize faults, and that are used by simulation and emulation. So at the end, I can say only safety matters. The rule to adopt here is not to buy a big car, but to be compliant to the standard. That concludes my talk. Thank you.
Thank you. Thank you very much. Thank you very much, Abdel. Any questions? You have one in Bristol.
So how you said it took about an hour to compile with these 1 million faults added in. How long did it take to actually perform the analysis?
The analysis, what we have seen, so this is a test case which is under consideration now. Right now, I have seen, it depends, of course, on faults. Sometimes the faults are very easy to prove or disapprove, and I have seen a runtime of 20 seconds, 30 seconds, but I also have seen runtime of 10 minutes.
Is that per fault that we're talking about?
That is per fault. So there is, to be honest here, we have for this particular test case I'm talking about, we have opportunity to consider all the faults at once. But I'm not running this for now. I cannot tell how this happened, how about this. But actually, I'm running here for per fault by fault. So the compilation is done only once, but later I'm running a regression of faults and how to say collecting the results. There is, of course, the next step is just to run only one single verification step for all the faults, or at least we can split. We don't have to consider all 1 million faults. We can also split to some smaller pieces, 100,000 or something like this. This is what we did before, and that was actually very successful.
So I'm struggling to understand how this is tractable, because how do you run them all at once and get figures for, you know, what percentage of them actually detected, and you know, if some of them are taking, well, I mean, even if they're only taking a second each, then that's obviously far too long. So you're obviously having to do them in parallel.
Yeah. So as I said before, this is the approach is actually not to run them one by one, just to run all of them by at once. This is we had values on this on different other cases, not for this last one that I have reported here, unfortunately. And the other feedback, or the other feedback that I have, is that we were running about 50,000 faults within all at once within some hours. So within I think 13 or 14 hours.
Okay, so I can see how you can find examples within that time of where the faults are not detected or where they are detected. But how do you get a figure for you know, the percentage of the faults that would be detected?
Here, if we go back to the setup that I have here, I'm not sure I'm following the, yeah, no, not this one. Here we go. So here in this context here, so we have a safety mechanism, and here actually what I'm doing is just we are introducing an assumption telling that, okay, we are not interested on all the paths where the safety mechanism will detect the fault. So just only give us 4 paths for which the fault is propagated up to the output but not detected by the safety mechanism. So this is just a run for the, let me see, the category DC, the dangerous category.
Okay, so it gives you, it can give you a list of all of those dangerous ones.
Yes, of course. Yeah. This is here we have on the report here we have a list of all the unsafe. These are all the dangerous how to say, dangerous faults.
Thank you. Thanks for the question, Anthony, and thank you for your answers, Abdul. Thank you for the presentation. Concludes the presentations for today. So just before we go, before we run off, a few thank yous. Thank you, Abdul.
Thank you a lot.